स्टार्ट कर दिया आ रहा है? हो गया। हेलो, आने में डिले लग
बहुत ज्यादा खुशी है।
हेलो
ठीक है, इसमें वो बंद कर दे, हम लोग भी खुशी होते हैं। हाँ ठीक है, इसको फिर इसको मैं अभी शेयर नहीं कर रहा, इसको बाद में कर।
ठीक है। वो अभी वही रिज्यूम हो रहा है या मैं
वो
वापस
मैं शेयर कर दूंगा तो वही
भाई रिकॉर्ड हो रहा है ना, कुछ मिला के बाद भी रिकॉर्ड
इतना सब
तो रिकॉर्ड तो हो रहा है, शेयर करेंगे तो आई थिंक प्राइवेट ही है नेक्स्ट में
कर दे,
तो
कोई
इसको
नहीं
कुछ
देख
चेंज
रहा
करना
है।
होगा।
पब्लिक जान दे।
हाँ टाइटल कहाँ पे
अभी क्या था ट्रेंड?
पेपर रीडिंग सेशन ऐसे 0 करके उसके बाद टॉपिक का नाम दे दो।
स्टार्ट करके सब ऑप्शन है,
ये ऑटोमेटिकली उसी तरह से पिछली बार पता कर। अच्छा एक मुझे ऐसा पोस्टर
पोस्टर म्यूटेड है। पोस्टर जब लगाया तो ऑडियो नहीं जा रहा।
इसका क्या नाम है?
इसमें नहीं खुली, इसमें खुली होगी तो शायद दिखेगा नहीं। सब तो कोई है मैं तो सब पीपीटी पे ही रखा था। वाला पार्ट उसमें से ये एज वाला एक पार्ट डाल देता हूँ इसमें।
पब्लिक ही है।
एक सेकंड, ये हट क्यों गया? क्यों गया ये? हाँ, नहीं गया। अच्छा बज रहा है वो। ये नहीं आ कैमरा नहीं है। ठीक है, वो भाग
डाल दे
एक सेकंड। ये
Hello everyone. Today we are going to read the GAN paper, which is Generative Adversarial Networks, along with the WGANs paper, and we have some prerequisites for it. So we will try to cover up fastly some of these prerequisites. So first up comes the KL divergence. KL divergence is a statistical method to find the difference, what is different between two probability distributions. Like if I have a one-dimensional single mode normal distribution and some other kind of and distribution like this, how we will have the measure of how different these two probability distributions are, we get it through KL divergence. So I will go through it fast. For a random variable, suppose x, which is of n dimensions, we have two probability distributions, p of theta and q of phi, where theta and phi are the parameters of those two probability distributions. These can be different from each other, so we are not dependent on the type of distribution. So as probabilities are between 0 and 1, by simply working on them, we get a if we multiply them consecutively for a large amount of time, they eventually converge to 0. So we will try to get a log likelihood of things. So we try we map it as log of p theta given x I and log of q of phi for x I. Now, for as a basic intuition, we would go. We want to find the difference between these two probabilities. So we can just, if we are trying to understand in simple words, we can take a difference of it, which would eventually give us this thing: log of p theta xi and q of phi xi. So this is what we call the log likelihood ratio. So here we can see this is the log likelihood ratio for a single sample. But but in case we have a large number of samples, we want to find the average values of things. That's where expectation values comes. So expectation values are simply talking a weighted average of these things. So we take xi multiplied by its probability. So we replace the expected value here. So we get so instead of doing this, we take in account now expected value of log likelihood ratio. Now, in case both of our distributions are continuous, this expected value, which is a sum over here, can transform into an integral. So this is what gives us the basic essence of KL divergence. Now, simply talking, now if we talk simply here, this can be hard to compute. So we take into account the law of large numbers, and according to law of large numbers, the average of results obtained for a large number of samples. Suppose we have a large number of samples for both these probability distributions, the expected value comes out to be somewhat this. We get to some back to summation. So this was the basic essence of KL divergence and how it works. So in this in the GAN paper, we also talk about Jensen-Shannon divergence.
Jensen's
I had a doubt in this. So you said that we are using log to scale up the values. So is this the only reason we are using log, or is there some other reason also? Like for
Clear log.
so for scaling the values, we could have used maybe some other function, I'm not sure which function would have done that job. For example,
Exponential.
1 by x. So x goes to 0, 1 by x leads to large values. So is it due to the fact that log something minus log of something becomes log of that divided by this due to this property?
Um, as far as I know, while we take up log, we can get into the log computations, which are far more effective. And also, the if we take exponential graph, it rises very fast, whereas the log is not that steep. So it helps us in that.
There is one problem with this scale divergence, and it is not symmetric. If there are some problems where we might need symmetric difference between divergence between two different probability distributions, we use Jensen-Shannon's divergence, which is basically defined in terms of scale divergence only. M here is just the mixture of both of the distributions that we have. We can see that if we interchange P and Q, this is a symmetric divergence we have.
So symmetric in what sense? Like
Here in KL divergence, if I compute so we can see the formula that if we compute it for, say, we interchange P and Q, we have Px multiplied over there, which makes it unsymmetric. If I interchange P and Q, it's not the same output that I will get.
this construction of Jensen divergence. So can you do some other construction? For example, maybe scale divergence of P with respect to Q plus scale divergence of Q with respect to P.
Yeah, this would also be symmetric.
Yes, we could also do that.
Are there some very nice properties about this Jensen divergence currently or?
नहीं देखा.
So moving on, we first try to have a glimpse of what generative modeling is. So before we move, we can model. Suppose we have a problem of classifying things. How would we like to train a model? Like if I suppose let's start with regression here. We have a number of points, and so if we take a neural network here, so or a linear regression here, it will try to draw a line through these points. So the next time we try to predict something, it goes on this line. So it eventually just tries to fit in these values and find a function that fits them. Suppose we have a classification problem and we have these points. Then it would try to draw a boundary here. So such algorithms that try to learn probability of y, which is our output for given inputs x, are called discriminative algorithms. And in contrast to them comes the generative modeling algorithms. So algorithms that try to predict probability of x given y, or eventually probability of y, are called generative models. So what they do is, instead of trying to just fit in, they try to have a sense of what are the distribution of these two things we are trying to classify. Like if we see here,
Why is the label?
what?
Why is the label? So this one, P of y given x.
Yes.
Okay.
So these are different from discriminative algorithms. Discriminative algorithms are just learning the mappings, whereas these are trying to, like if we have some distribution here, some here. So these will try to learn how these are distributed along an area. So then we can use Bayes theorem, which is written here, to just simply get what type of distribution is, what type of label this would a certain point would have. So here comes the generative modeling have this advantage. Now since it knows for both the different types of distribution, it knows how they are distributed. So if we want, we can generate a new point here. We can obviously say, since this distribution we have fit in, and this also, we can create new samples. Moving on, like here we see it has instead of drawing a single line between these two distributions, it has actually identified how these distributions are varied and how they are scattered throughout our parameters. So how do generative modelings work? In most cases, they predict the maximum likelihood estimate of for a probability distribution. So maximum likelihood estimate is, in simple words, what I would say is for what value of a variable this would most probably lie in our distribution. So we try to maximize that value that increases our log probability. That log probability is called the likelihood, and we try to maximize it. So now we get to how generative models can be classified on this basis of maximum likelihood. So although we don't know much about these different models, we will try to take a glimpse of how they are different and why did GAN was introduced. So first we have the likelihood on the basis of maximum likelihood, whether that density function can be explicitly placed out, like we can write a proper function for our distribution. If we can write, we can call it an explicit density function, otherwise an implicit. In the explicit also we have tractable, which is exact function of the distribution we can extract, and approximate. Approximate is like we introduce error terms, like we will see further in our variational autoencoders. So moving on, these have some disadvantages due to which GANs help to solve. So first we move to explicit density generative models. So we have first we have fully visible belief nets. These are of the class explicitly tractable. So what they do is they use the chain rule of probability, and they just use a chain rule of probability and do not use a latent space. So what the advantages of using a latent space is, for like I have an image here, and it is an image of a person. So a person has instead of simply, if we try to divide it in pixels, we would have a large number of pixels, like 256 into 256. So looking at these pixels alone, looking at a single pixel, you would not know what does this represent. But if we try to see in simpler terms, what are the things governing this image? This can be the skin color, this can be an hair, the eye color, and the face shape. Such variables that define how our image is being characterized. There are certain set of variables, and that variables we can call as the latent variables. So what these latent variables are, they may have a lower dimension, they have a lower dimension than this dimension, and they are able to capture the essential characteristics from which we can create such an image. So these fully visible belief nets do not use a latent space, due to which we are not able to capture the essence of something. Then we have some other types of generative models like NICE. What they do is instead of using a simple instead of taking what we can say as a density function, they apply some transformations, like they define the label as output as y is equals to g of x, and then they try to apply some transformation. They say probability for given x is equals to probability of So they are trying to apply a transformation here, where they say they just define y is a function of g of x, where and then we can say probability of a given x can be written as this. Now we don't know how this transformation works, for we are not looking currently deep into this, but they have some limitations. Like what we are seeing here is a determinant, or and that too of a Jacobian. So first that should be a tractable, and this transformation should also be invertible. So these also raise certain types of limitations. Then we move to VAEs. So what VAEs do, like
I had a doubt in this previous slide. So it will nets. So where is the net part here? So which part of the this thing the neural network is learning? Is that px2 given x1? Like, where is the neural network taking the role? Is it learning that probability matrix or what?
so
I guess it starts from some.
It just takes the first probability of first feature and then compare with the second term. It's just probability of second feature with respect to first.
It's not the so if we take the image x1 to xn are in the features, no, they are the pixels there, no. I think it starts from the first pixel from some Gaussian distribution px1. Then it uses a network which knows that if I have this pixel, what should be the next pixel. It's like kind of an RNN. Starts from the first word, predicts the next word, takes the next word, and the first word predicts the third word. I think it was like that. Okay. What was the second network?
second was networks like NICE that introduce some transformations.
VAs are like this one, they take that normal distribution and transform it to some complicated. Let me see.
But maybe they are not good with it.
Okay.
So now we come to VAEs, which is an approximate. VAEs approximate the density function. They can't just define it completely. So what they do is they introduce latent variable z, and they try to approximate the posterior, that is probability of z given x, where z is a latent variable. So if we try to write what they do is again for maximum likelihood they will try to maximize this, and now since we can't so that this density functions we can't exactly find out how to maximize this, like since probability of x is probability of x given z to marginalize z, we don't have we can't exactly find out what type of what type of latent space we would require to maximize this. So they try to take an lower bound, evidence lower bound, which we can in turn minimize the lower. So we write this as log p of x is greater than or equal to log p of x. So they try to, this is the evidence lower bound, and they try to in turn minimize this. So as long as we maximize this, sorry. So as long as we try to maximize this, we get an approximate function of how latent variable distribution can be modeled.
Actually, I'm not able to build the intuition of each term we are getting the script.
What?
I mean, what is the significance of introducing each term, right?
This term.
All this loss.
And what is that Q? When you didn't define it in there. Q.
Yeah, the basically the second distribution paradigm.
Q z given x.
And Q is like the decoder. It's no Q is like it's like the encoder. So it's taking X and giving Z. So it takes X and gives up probability assignment to Z.
Of later
And what is P?
P. P is taking
These
Z
are
and
like
giving
you-
X. So it's like the decoder. It's saying that if you take a Z and if you give an image, maximize its probability. And also P of Z. And P of Z is, I think, the normal distribution. So it is saying that so Q of Z given X is the encoder. It takes an image and gives a probability to the latent vector Z. It is saying that do a KL divergence of that with P of Z. P of Z is some distribution which we have defined earlier.
Yeah, it is.
For example, normal distribution. So it is saying that bring the distribution.
P of z is a real distribution, right?
No,
No, P of Z is
Q Z of X is the real distribution.
Ah.
P of Z is the distribution that we have assumed.
So P of Z you assume to be some tractable distribution from which you can sample, for example, normal distribution. You are saying that take the image, give a latent vector, but also try to make the latent vector a Gaussian kind of variable, so you can sample it later.
Yes, that was the difference between the normal A and the B.
And normally you don't have that term, KL divergence term.
Yes, the paired divergence.
So the main thing here is it is asymptotically incorrect. Like we can't exactly, in any case, unless we have infinite samples, exactly predict what was our distribution. So then we have Boltzmann machine. Boltzmann machines are physics inspired. They use this type of function here. So what the difference here lies is, since this is also not explicitly tractable, we can't find what z distribution should exactly be. It tries to use Markov chain, and in Markov chain, each of its output, like zi, is always dependent on z of I minus 1. What the previous output was. So if we try to calculate here, if we try to make an inference here, first it will carry out the inferences on all its previous, like to predict the ith pixel, it will take all the previous pixels and run Markov chains on it. So this makes it unscalable, since it require for a simple image only, it would require a large amount of steps.
Okay, good. What was the limitation that is created for the V?
It was asymptotically incorrect. Like we can't exactly find what the latent distribution should be so that it matches our sample distribution.
I think you are assuming at some point that PZ is normal distribution.
Yeah.
So
okay, so you can't.
you are constraining.
You are constraining.
And anyways, this is the lower bound. So if you maximize this, you are still maximizing the bound. I think that's not a big issue. The big issue is that you are assuming that TZ is a normal distribution, which it might not be. But if you assume some very complicated distribution, you can't sample from it.
So you don't know for the
Real,
you don't know the real distribution.
you assume that, let us assume it's a normal distribution so that we can sample from it after training.
Next.
What's that Z part in the Boltzmann machine? E
Uh,
to the power minus EX comma Z.
so the Z is our current latent variable. So to predict it, we find a summation of all. Wait.
So Boltzmann, so you are using Z here. So Boltzmann machine is also using a latent variable or what?
Yes.
Okay.
So here comes GANs. They are asymptotically correct. Theoretically, they are asymptotically correct, though not in practicality. They use a latent code of using latent variables. They don't have Markov chains, so are scalable, and they are able to produce best samples because they don't use traditional loss functions. Instead, they try to take two networks and play a minimax game between these two. So how GANs work? So GANs are an adversarial network. Now that we have learned how generative models work, we take two models. We take a generator and we take a discriminator. So the primary objective of generator is, suppose we have a latent space. It can be a single mode normal distribution, and we can call it to be zero. So what a generator does is it takes in these and gives out it takes as a latent variable and gives out a sample. So this is a function that tries to take in keeps taking in latent variables and try to make out samples. So obviously this will have to be trained, else it will not know how to produce correct samples. And discriminator is like a cop here. It receives two samples, like it received a real image and it received a fake image. So it will try to predict the received image is real or fake. So in case if it is a fake, it will assign it value 0, and if it is real, it will assign it a value 1. So this is like a counterfeit games. A generator is trying to produce fake notes, and a discriminator is a cop that tests whether the note is a fake one or a real one. So what they do is they play a game with each other. The generator keeps producing fake notes, and discriminator keeps trying to find the which if it is real or fake. So now here we have it took an input. The differentiable generator function is a differentiable function. It took an input noise z and produced a sample using its function, and that sample seeing in the right side then went to the discriminator. The discriminator then tries to make d of g of z near 0 because it is a fake one, and whereas the generator which is trying to fool the discriminator, the generator wants to make d of g of z near 1, meaning the generator wants to fool the discriminator to think that the fake sample he created was actually a correct one. So and in case the sample is actually from a training distribution, like on the left side here, when X is sampled from our training distribution, when we apply discriminator on it, since it is a real one, it will obviously try to make it near 1.
Okay, so the generator has no access to the real images, no?
No.
So it is like it will take time to train.
Yes, it does take time.
How are you ensuring that the generator and discriminator both are looking in the same latent space?
No, actually the generator takes in
Suppose we start from a random noise and generator is not trained at the starting, it will produce some very blurry image, some Gaussian distribution, the Gaussian image. Now,
What if the distribution not Gaussian?
so like, so if you take a random vector z and you apply some random transformation step, you are guaranteed to get a normal distribution. Anyway, suppose you don't get a normal distribution, but why sure you won't get that phase at the starting of the process. It will be easy for the discriminator to just go and say that it doesn't look like a face, so let us ignore this, and it will easily identify it.
Yeah, basically the discriminator will converge faster than
So I think it was one of the problems that discriminator is like more like discriminator is just a classifier. It has to just see an image, say whether it's a fake or not. It has an easier job to do, while the generator has to create images out of like near. So. So, you can comment to the what was that diagram in the left hand side?
so left hand side is what happens when the discriminator is applied on a real sample. It tries to make it near one since it is a real sample.
Oh, okay.
So now we come to the generator networks. Generator networks can be CNN based or can be deep neural networks. Here what the generator outputs is a sample X. So the thing is the generator should be trainable for any size of the latent for any what I can say dimension of the latent space. So so that we can actually it learns. So make sure that it learns. So
What do you mean by still not clear in this part? So for first line is okay. So the generator must be differentiable for back propagation. Fine. It can be designed to accept a latent vector set of any dimension.
the thing is, suppose we have the real samples, which is of so we have real dimension. We have a real sample which is of the dimension x of n, and then we have z. It can be of up to m dimensions. So we have talked about how manifolds work, how latent space works. So in case where we had 256 by 256, we saw that the latent space, which essentially captures the different characteristics of this image, was was of a very low dimension than the actuality of 256 by 256. Here we are also saying that the latent space from which we are drawing our samples has to it can be of any dimensions. Like it can.
It should be and can be trained to. So if you train it at some specific dimension, then it will work for that dimension, no?
basically you can't change the dimension of the latent space after you have trained the model.
So
You have to find the architecture, then you can't change the dimension of the latent space.
suppose you take a dimension of 128. So my incoming neurons are 128 separate neurons. Suppose you take a 256, how would you pass it through a 128 space? I think the point here.
This is fixed here.
Yeah.
No,
X
we're
is
talking
fixed.
about Z.
The Z will be fixed or Z can vary for a single architecture.
By varying, he's talking about dimension.
Dimensional variations.
I mean, it should be fixed here.
Yeah.
So, but then here you have written that it can be designed to accept a latent vector V of any dimension. I think it should have
Like
been.
for making an architecture.
Oh, so
not
it should have
actual.
been some other wording like can be trained at any dimension to map at any other dimension.
So
Fine.
then came the second point that it should be to run an inference. It should be we need to be able to calculate the intractable probability of z given x. Like we should be able, if our original distribution is this, we are able to come up after several rounds of training to our specified distribution. So then to play this minimax game, we define a value function here. So which is oh, it's written here. Like these are the so we define this value function here. What we for a discriminator, its first thing was it if it is getting a real sample here, it would try to maximize this thing since this is a real one. And in case if it is a getting a fake sample, the fake sample would not cause change any in this term, but this term would decide how the discriminator takes in. So the discriminator will try to make since the discriminator tries to make d of g of zero, it would try to make this term as small as possible. So here so So here the generator, which is the generator's work is to fool the discriminator. So since the discriminator will try to maximize this, generator will try to minimize this function. So we can define separate losses for this. If we define this as the loss for the discriminator, then we can simply say the loss for the generator can be minus times loss of discriminator. Since we are, if we, the discriminator tries to maximize this and maximize this, and the generator in turn tries to minimize this.
So, like, is this like end designed by the authors, or is there some convergence criteria that given distribution in infinite time, this game will converge to the like the generator will become super powerful and the discriminator won't be able to discriminate anything. Like on whose favor is this game? Like if I see it's like
the game is in favor of discriminator because this is a log function here. Initially, we see how logs work. So, in case it is a if it is a negative log, it would go like this, or else it would go like sorry. So initially we see here the generator which is minus j times t. So instead of trying to maximize this, it tries to minimize this. So initially the generator has very large log, so it is able to catch up quickly, but even in the starting it is very biased. The whole game is biased towards discriminator.
No. So I get that point. At the starting, the whole thing is biased towards a discriminator. What I'm asking is that if I run this process for long enough, do the authors guarantee that we are giving more chances to the generator to learn? Like this seems to be giving equal gameplay to both of this generator and discriminator. In such a fashion, like both of them will keep on improving.
So what the authors did here was that if we see for number of training iterations, they inside each iteration they tried to run. Please don't write it. They try to discriminator. They try to run the discriminator first for k times, so that for if the generator and discriminators are here, the discriminator for each iteration, if the generator moves this, the discriminator tries to move k times more. It has k more training iterations. So, but when they implemented it, they had k equals to 1. So as to give both of them a fair chance. But since in the starting, the log is here, it eventually, if we see, as we move till here, the changes in generator become very small.
Change in generator or discriminator?
And the change in generator.
Okay.
That would.
Please explain that point.
So initially we see that generator will have large changes that will help it to catch up, but eventually after a long number of training iterations we will see when generator reaches in this region, the generator will not be able to have a large magnitude of meaningful change. So that will cause a problem here, for which we will make amendments in this. So for running a discriminator, we sample m noise samples and m examples, and we update the discriminator by using this exact function I just told. We run this. If I am trying to drop.
When you update the generator, suppose you are using the loss for the generator.
Yes.
That time you will only backpropagate the weights of the generator, no?
For the generator, yes.
And when you suppose you are calculating the loss for the discriminator only.
We will not backpropagate to the generator.
Okay. Both of them are getting better and better. But at some point, the discriminators should be like. It should be clueless at some point.
Yes, that's where we come later. If suppose we had infinite iterations and we reached an optimal discriminator, then the discriminator would not be able to differentiate between real sample and fake sample. So it will randomly assign. Then the optimal discriminator value for any given x will be half, because it will not be able to identify if it is a real one or a fake one.
The fake set now become the real.
So we take m training examples from this, m training example from which is this g of z, and we run for k steps for this discriminator. We had k equals to 1 in this paper. So it did two things. When it is from this, it will try to get it 1, and when it was from this, it will try to get it 0. We backpropagated here, and we backpropagated till only here. We didn't backpropagate here. And then we run, after we had run the loop for discriminator, we run for generator. Now again we run this entire thing, and now we backpropagate from here to here.
So the discriminator weights will not be generated in the second iteration.
Not to be that probability, no?
But since that probability is computed using the generator and discriminator both, so how that gradient will be calculated for only the generator? Each में जो discriminator
I think the weights of the discriminator are frozen for that amount of time. You're correct. How do you go back through that?
Yes, so they are tracing back through the discriminator, but they are not updating that.
They are not updating that, but we
It goes through that
goes
path.
through them.
Okay, fine.
I have a question like, why don't we take an already very strong discriminator instead of showing again?
How do you make up a very strong discriminator if you think?
First of all, for many iterations, just train discriminator. I mean,
Against
take
what
a
would you
large
train?
sample of maybe AI-generated images and real images. Maybe.
Can you explain? Well, repeat please.
Let's say like the AI of thing, and then use the discriminator in this model. But then the generator will not get the time to space.
I think there is some problems related to that. So if the discriminator becomes too powerful, the generator won't be able to learn. So if you see, suppose you are trying to create images of, let's say, cats. At the starting, suppose you train a discriminator in the CFAR dataset, and it knows what are cats and what are not cats, and what are the fake images. If you just give it a random, now the job of the generator is to directly generate an image of the cat in this guy. So it is very tough now. But if the process is on like equal parts, the discriminator is also learning slowly, the generator is also learning slowly.
Basically, the AI is
Still not sure, like, correct out. So they are using that K hyperparameter, no? K equal to 1. So it's like that only. If you set K is equal to 100, you will train the discriminator for 100 times steps before you train the generator. So you're effectively training the discriminator. But in practice, I've seen that K equal to 1 is the best one. I think they have reported, see, we use K equal to 1. Okay, so they have mentioned it's the least expensive option, but it's the most stable option also.
That's one of the drawbacks of GANs. When we cover WGANs, we will see that they can be trained the discriminator can be trained longer without having any issues there. When the discriminator is very good at classifying the fake and real images, and both the probability distributions are completely disjoint. We are not showing the calculation here, but the Jensen-Shan's divergence actually flattens out at that point. So it doesn't provide enough gradients back to the generator. That's one of the problems.
In this, we take D for a long time.
Yes, K for a long time.
K
Yes,
Like-
even with K equals 1, there are problems in training with GANs. We will see that.
No, so suppose you are training at K equal to 1, you are saying that the problem of GAN is the generator becomes too good, but not on a very optimal level, at a suboptimal level, and the discriminator can't identify whether it is real or not, something like that.
So if the discriminator becomes too good at classifying between real and fake, then there's a problem with giving enough gradients back to
That's
generator.
correct. But suppose, no, I'm still not able to like understand what's the problem with this. Like you just said that if we increase K, so what was the problem if we increase K?
The discriminator becomes too good. That's the problem. We want it to be just a bit less than optimal, exact optimal.
Okay. And what if I don't increase K? What is the problem with that if I put K equal to 1?
There are still chances that it might end up becoming good depending on how the weight landscape is. If it ends up in
I think it's I've seen something like that. For example, if you in the case of GAN, there comes a stage where the generator is generating good pictures, but not as real as the real ones. But the discriminator is not able to identify which are the reals and which are the fake.
So
I guess he said no that if you go towards that process,
Slow, basically.
so the work done, the updates done in the discriminator becomes slower and slower, something like that.
So for that, we can increase the key.
But increasing K leads to instability.
Where it will lead to instability.
In this thing is it's a very unstable to play.
To solve this problem, we will eventually change the generator loss function. So this is how the training goes. In the actual paper, they had given a proof. I can tell if you want of how optimal discriminator and optimal generator. We are 100% sure that we will be able to get to an optimal generator for sufficient training examples. So just seeing what optimal generator is, an optimal generator is able to produce a distribution where the generated distribution is exactly equal to our sample distribution. And for such a distribution, the discriminant will not be able to tell what if it is a real or fake. So it will always get us half. And they also had a proof of what would be the first they found an optimal discriminator, and from there they came up with a proof of optimal generator. Simply stating an optimal discriminator, they say, would be this would be the optimal discriminator. Since we saw the problems of how GANs they eventually get saturated, so we have to solve these problems because there was also a problem with GAN, like we are not able to quantify this, like how by playing that game how we will tell if it is a good distribution or not. We had no proper loss function.
We have a prerequisite for WGANs. Let's just see what a K-Lipschitz continuous function means. Here, this for suppose this is the definition of a K-Lipschitz continuous in one-dimensional function. For if we bring C1 and C2 close, we can also define it to be a derivative. And for multi-dimensional functions, we can define it for like this. For if the gradient norm is less than equal to k, that's our K-Lipschitz continuous function. And there are problems with GANs, which we just discussed. The training is unstable and there is no way to monitor the loss function. If it might, we cannot know if the model is training or not, because the loss doesn't necessarily decrease based on how good the generator is. So we use a different loss function, and we also remove the sigmoid layer from discriminator for which we used to classify. So let's see. The main problem with GANs was where if we train the discriminator a bit too much, it just stops training stably. This is a new loss function which they defined, and instead we just take the expected we take the discriminator output. We had generator and these were real images. We just take the direct raw output without any sigmoid layer. It's just real. It's just the real value output from anywhere between -infinity to infinity, and we just sample some values from the generator and we sample some values from the real images, and we just calculate the difference between them. This is actually called as called a Earth mover distance, which is different from the Jensen-Shannon's and KL divergence we saw.
Can you please repeat that thing? How we are calculating that?
Basically, we have a generator. We take latent variable and we get an image, and we pass it through a discriminator. Here the terminology is actually not a discriminator, it's a critic. They use the term critic, and we have a set of real images from a training data, and we pass that to a critic as well. Critic has just one job. For real images, it is supposed to output a large value for real images, and for suppose we take m samples from both, so we get an output for real images for m samples. We want it to be large, and for generated images we want it to be small. So we basically take this difference. Because this difference basically helps it to maximize the score for real images and minimize the score for generated images. It should be as negative as possible. It should be as large as possible.
You are using the same variable in there, so I assume that you are passing images one by one, no, 1 real, 1 fake, 1 real, 1 fake.
M is the batch size. Yeah.
So I'm asking that suppose you have a batch size of 36, so you are passing 36 real images and 36 generated images, no?
Yes.
Okay.
There is one criteria which was enforced by the authors, and it's basically the same thing with the one Lipschitz continuity criteria which we saw at the start. The reason for this is basically that earlier we saw how the discriminator for GANs was causing problems if we train it a bit too much and it becomes too good. So having the K-Lipschitz continuity, this criteria, this basically puts a limit on gradient norm. So it doesn't allow it to train too quickly to two optimal values. But they used a technique for actually satisfying this criteria, which was to just clip the weights between minus 0.01 and 0.01 for all the parameters of the critic. They admit it was a bad idea, but it still worked and it gave results.
So basically the condition is to clip the norm. Basically they have an upper limit for the norm.
Not actually the norm, for each weight.
Yeah. The Lipschitz condition says that the norm must be
Yes,
one.
norm must be less than 1, but they don't directly, the gradient norm must be less than 1, not the norm of the weights.
Okay.
The gradient norm must be less than 1, so they directly don't enforce it directly, they instead enforce it through clipping the weights.
I'm still confused. So weight norm, gradient update norm should have a legit norm of less than 1, something like that.
Yes.
Why so?
That's mainly because to prevent the discriminator buff from becoming too good too quickly.
But why doing so? You are also preventing the generator for becoming good, no?
The generator is trained they are trained in iterations, right? The first only the discriminator, then the generator. So while training the generator, if discriminator is suboptimal, not necessarily completely optimal, and it's not too bad either. If it's suboptimal, it can still provide training signals to the generator.
But the training signals will diminish due to this clipping.
It's a terrible way. They actually claim that the weights actually end up being complete either 0.01 or just minus 0.01. Most weights end up being at those ends only. Yes. the the training policy is almost the same as what we saw for GANs. We sample it from a batch size of m, like we saw here, and they instead use a RMS prop, not an Adam or momentum like the previous one, and they actually found Adam to be less stable than RMS prop for this case, mainly because of the weight clipping as well. This problem is there is WGANs. We can see the graph on the right. The weight clipping ends up makes the weights just scattered towards the endpoints, and the we see the different approach, the different paper of WGANs with gradient penalty. Its weights are properly scattered as a normal distribution. What is gradient penalty? So
Can you take with the
yes,
so
second graph.
it's the gradient of and it's on the log scale.
Yes, we see there is also that. Just a second.
What is on the x-axis?
Wait a second. वो ग्राफ नहीं है ठीक है the suppose discriminator is 13 layers deep here.
Okay.
So the layers till towards the end, those the start actually, they end up the gradient norm actually ends up going towards the end. The gradient norm basically shoots up to a very high value, but you are still ending up clipping it. So we are not allowing it to update when it actually wants to update. So the red, purple, and the green line. We define a new loss function here. Suppose we have real data sampled from PR, and we take a latent variable z just like in GANs and WGANs, and we take a random number here sampling from a uniform distribution, and we generate this new image, which is basically an interloop between the generated and the real image. And this was the critic loss we had in WGANs. So what we do now is we directly enforce the gradient penalty itself, which we wanted to be less than 1. So we enforce that criteria directly, but it's using this interlooped images, not the direct images.
Okay, so you are not now you are not clipping the weights. You are having a penalty in the loss. But by using this mean, imaginary sort of a weighted average of the given and the generated one in the gradient penalty.
Yes.
Why?
Just a second.
You are passing it through the discriminator, getting the gradients, and then taking the norm for the penalty.
Yes. कहाँ था उसका नहीं है शायद उसका ये प्रूफ था which was a bit too big to go into depth, so we leave it for now. And this was a training policy. We can use Adam here. This even actually works without batch norm, which we need in GANs and WGANs. This can be trained without batch norm, and this is basically what we have here. Okay.